So good afternoon, everyone. Thank you for coming to after lunch seminar on Wednesday and right before the Clinton big announcement or big presentation. This is the distributed utility scale solar workshop. We're focusing on grid integration here. My name is Kevin Lynn, and I lead the systems integration team as part of Sunshot Initiative, DOE's Sunshot Initiative. We've got a great panel here this afternoon focusing on grid integration. I wanted to bring up a few quick points before we get started. From DOE's perspective, obviously, for those of you who know the Sunshot Initiative, we've had a lot of focus on the cost of our technology. So in terms of whether it be $1 per watt for utility scale, $1.25 per watt for commercial scale, and $1.50 a watt for residential scale, all by 2020. So another big piece of that is also the deployment piece. So we feel like by the end of 2030, we could potentially get to the point where we would be on the order of 14% by energy coming from solar electricity, from PV and CSP combined. Now obviously, one of the big players within that is grid integration. If you don't, you can get the cost down as low as you'd like, but if you don't solve some of the grid integration problems, you can't reach those kind of deployment goals. So I think we all realize this is a pretty important crucial goal that we need to overcome. As I said, I think we have some great presentations that are going to cover both the utility scale and distributed side. And I think there's a couple of things I'd like the audience, to consider as questions, because I think we're going to have some good time for questions at the end of this whole session. One was brought up during the first general session the evening on Monday, talking more about which distributed or utility scale, which is the way this industry is going to go. And I know I've heard from several from the utility industry. They think some people thought it'd be on one side. I think some of the talk from that session talked about looking at maybe distributed becoming a more prevalent way to go, depending because of the way the costs were coming down. So I'd like, just as a group, as we go through some of the presentations today, sort of to think about where you think, where is the market going to go, either in the near term and the long term, in terms of more on the distributed or the utility scale side. I think the second piece that I'd like to bring up too, and something that we're considering more here at DOE, is obviously, solar is a very small part of the entire utility system, and we need to play with not only the utilities, but all the new technologies that are coming to be integrated with utilities, whether it be electric vehicles, whether it be smart grid technologies, energy storage, etc. So how does solar play with all these other new technologies that are being developed? So think about those questions as you hear some of the great presentations that we have here today, and let's go ahead and get started. So here's a list of the speakers that we have for today. I think we're going to start with Robert Broderick first, though. So let me introduce Robert Broderick. Robert is the technical lead of distributed grid integration programs at Sandia National Labs. Prior to working for Sandia National Labs, Robert worked as a consultant for TRC Engineers, Inc., focused on solving problems for PV project developers and performing comprehensive grid integration studies for utility clients. Robert worked at P.M.M, the largest IOU utility in New Mexico, as the manager of renewables, and developed and managed the successful customer-side PV program, which is expected to achieve over 20 megawatts of new PV installation by 2012 in P.M. service territory. Robert also worked as a senior power engineer in P.M.'s distributed planning department and customer generation department. Robert took a lead role in writing New Mexico's new interconnection standard utilizing industry best practices and IEEE 1547. Robert is a professional electrical engineer, received his master's degree in power systems engineering from New Mexico State University and a BA in physics from the University of Colorado at Boulder. Please welcome Robert Broderick.
Great, thank you very much, Kevin. So as Kevin mentioned, I've worked in the renewable energy business for quite a few years, and it's my pleasure to be here this afternoon to talk to you. What I'm going to discuss today is a paper that Abe Ellis and I, my partner at Sandia, he's been at Sandia for many years, brought me on about 6 months ago, so I've been at Sandia for 6 months. And I'd like to talk today about our evaluation of alternatives to the FERC SGIP screens. That's the small generation interconnection procedure screens for PV interconnection studies. So let's go ahead and get started. So distributed generation, in terms of the rules that you have to be concerned about, there's primarily two jurisdictions that we're concerned about. The first is the FERC jurisdiction, utility side generation. Typically this is what follows the SGIP process, and it's for 20 megawatts or less. The rest is covered by state jurisdiction. This is typically customer side generation. The rules vary from state to state. However, 10 megawatts is a typical upper level for what can be covered under this jurisdictional area. So the goal of these interconnection procedures is to establish a consistent interconnection process, but its primary purpose is to determine fast tracking of applications. And almost all the rules that I know of in the United States limit that fast tracking to 2 megawatts or smaller systems. Now what's really good about the fast track process is that, one, if it passes that screening process, one, we expect no system upgrades, so the amount of money and time is significantly reduced. Safety and reliability are not materially affected, and it makes sense to avoid unnecessary study cost and processing time. So the purpose of the screening procedures is to balance the need for efficiency and technical rigor. And the goal of the process is to expedite interconnections. It's also to identify interconnection requests that are most likely to impact the electric distribution system and need further study. It's also to avoid unnecessary interconnection study costs and delays. So what I'd like to talk about today is two of the screens that we think are the most ripe for being reevaluated and to evolve and update them. No surprise, the first one is the 15% limit of aggregation generation on the line section, and the second is a very important screen for distributed generation, and that is the limit to 20 kW of aggregate capacity on a single-phase secondary circuit. So let's talk first about the 15% screening criteria. This may be old news to most of you or new news to a lot of you. The 15% screening criteria was pretty much came up with in terms of a peak to minimum load ratio. So the example we have in the following diagram is a typical residential commercial profile. You can see that the peak load during the middle of the day is about 5.6 megawatts. The minimum load occurs during the early morning hours when it's still dark, and we're at about 1.3 megawatts. So the 15% screening threshold the rationale for it was that by setting the threshold, we could look at both. We could be prepared for voltage issues, protection miscoordination, unintentional islanding, and other potentially negative impacts. If there was negligible, they would be negligible if the amount of DG on the circuit was certainly smaller than the feeder capacity, but also less than the feeder load. So since on most substations in the United States serving a variety of feeders, the minimum annual load is approximately 30% of the annual peak load. So the actual ratio varies, and we'll show you some data on that in a minute. But based on this generalization, the 15% penetration threshold was established, i.e., 1/2 of the 30%, as a conservative screening threshold. So what's the significance of this for PV? Well, first of all, as we get increasing penetration of PV on the distribution circuits, we're finding that this is the screen that typically causes the interconnection to fail the screening process and have to go into a study process. And we found by looking at a lot of the feeders where they have gone to a study process that the screen may be overly conservative for most PV installations. The other reasons why it's significant for PV is the vast majority of DG interconnections that are evaluated under these procedures are solar PV. And finally, probably the most important piece is PV has a unique output profile. It's strictly a daytime diurnal cycle. And why is this important? Well, it's important because the voltage impacts that we're concerned about are going to happen when the PV output is at its maximum during the daylight hours. On the other hand, the PV system is going to be producing substantial amounts of power when all the loads on the circuit are also well above their nightly lows. So an alternative technical screening criteria comes to thought and to mind, and that would be to look at the minimum daylight load, where daylight is defined as a period between 10 a.m. and 4 p.m. So here's a collection of data using 500 residential and commercial feeders in a southwestern city. And what this data shows is the comparison between looking at minimum load data only based on the 24-hour, that's the red that you're looking at, or looking at it based on daytime minimum load. The main takeaway is to look at the two columns to the left. Over 80% of the feeders are greater than 30% peak to min load ratio if you use daytime. If you use the 24-hour, you're only at 55%. So this, of course, raises the question, what is the best way to establish the threshold? It's going to be difficult to establish a minimum daytime load threshold because you can see the spread of values based on, say, feeder topology or some other criteria. So the logic would lead one to conclude that what we need to get at is the feeder minimum load. And for many utilities, this is not a problem. If they have supervisory control and data acquisition systems, they're gathering that data, and they can use that data to determine the minimum load. So one of the suggestions for modifying the 15% screen, which I'm sure a lot of you have heard about, it's certainly in the FERC docket right now, based on a SEA petition, to look at the 15% screen. And there's two ways to look at how we could modify that. First, we could, of course, increase the peak load percentage, i.e. go to 25 or 35%, for example. Or probably more appropriately, to look at a percentage of the minimum load. And what's currently in front of the FERC is to establish that threshold based on 100% of minimum load. So as you can see in the example listed here, we have a 5.6 megawatt peak at the top. And if you use the minimum load of any hour of the day, you're going to be around 1.3 megawatts at 5 a.m. in the morning. If you use the daytime load, you're going to be up to 1.8 megawatts. So we're looking at a 500 kW difference. Now that may not seem like a lot in the big scheme of things. However, you must remember that in order to be in fast track, you have to be 2 megawatts or less already. So we're talking about a significant increase of those applications that are 2 megawatts or less that can make it through the screening process. So how could this modification actually be put into place? Well, first of all, you don't want to lose the advantage of the 15% screen. It's been shown to be effective in terms of taking the vast number of interconnections that come into place and allowing them to go to fast track. So you leave that in place. And then what you do is you have a follow-up screen, which is shown in the yellow bubble here. And you look at all the proposed generation on that circuit, including the actual interconnector that's under study. And as long as that penetration level is below the minimum daytime load, it continues on to a fast track process. So this need not be an overly complicated modification of the screening process. There's a lot of precedence going on with California Rule 21 and also, as I mentioned, the FERC petition to roll this area, which is in yellow, into a supplemental screening to handle it more efficiently in the supplemental versus initial. Okay, so now I'm going to jump to the second screen, which is probably more applicable to true distributed generation, i.e. Solar subdivisions. This screen is set at 20 kW, and what this means is if you have any interconnections, say for example homes in a subdivision, that 20 kW has to be smaller than that for all that's aggregated on the secondary of a distribution circuit, or it has to be studied. Now there's actually a lot of problems with this screen, but the most obvious problems is it's a one-size-fits-all threshold. 20 kW does not make a lot of sense when typical distribution transformers for solar subdivisions or any subdivision, those transformers range from 25 kVA up to 100 kVA. Secondarily, there's a lot of small interconnections where you've only got 1 or 2 customers connecting to, say, a 10 kVA transformer on a pole. So both of these lead one to conclude that there are definitely some problems with that screen in terms of its one-size-fits-all threshold. So one of the things that we did in New Mexico is we evaluated a subdivision. I won't go into all the details here, but this is basically how you go about doing it. We evaluated a solar subdivision with a 50 kVA transformer. That's what you see off on the left. And this was 11 homes. And we basically did all the analysis on what the secondary circuit looked like, the types of triplex cable, the number connected to a pedestal, and also looked very importantly at the standard utility operating practices. Once you put that model together, you get a PV current flow model that looks something like this, where you can see where all the various voltage rises are going to occur on the distribution transformer. So in this case, we had 11 homes, and I'll have you take note of the far right current input, which is at node 8804. So we had to make a lot of assumptions before we put this modified screen together, because you're looking for a worst case scenario. So here are the worst case scenario assumptions we made. One, all 11 PV systems, i.e. one on each house, they're all producing maximum power in afternoon sun. We assume that nobody's home at the houses, so it's going to make it for the worst case condition. All the loads are off. We're going to assume the voltage profile is flat. We're going to assume that the utility has already raised their nominal voltage to 123 on that circuit, and we're going to assume that the LTC at the sub is already at maximum raise, and so the nominal voltage at the sub is 124.5. So that only leaves us 1.5 of voltage headroom before you exceed the ANSI threshold for range A. So what we're doing here is showing a worst case scenario and then asking how much PV can we stick on this solar subdivision before we raise that voltage above ANSI specifications. So here are the results. Notice the far right is the load in the PV, that's node 8804. And you can see how the voltage rises from the substation transformer on the far left to the distribution transformer, then to the pedestal, that's the secondary voltage rise, and then finally the service voltage rise to the home, hitting exactly 126. This occurred when each of the homes had approximately a 3 kW AC PV system on their roof, so we ended up with 33 kW. So this similarity in size between the maximum PV capacity and the distribution transformer size suggested a simple screening threshold for assessing voltage rise problems. And that threshold was basically to look at the aggregate size of PV systems should not exceed 65% of the kVA of the distribution transformer serving the systems. Now keep in mind, this screening is it's simply a threshold, so it's based on worst case scenarios, and it helps to ensure that there is a simple and quick new screen that will flag interconnection requests with high PV deployment levels at higher risk and needing further study. A version of the screen was adopted and implemented in the 2009 New Mexico Interconnection Screening Process and Interconnection Manual. So in conclusion, we have shown two examples of alternative methods to how the SGIP interconnection screening process will allow for a more rigorous upfront technical evaluation to identify potential system impacts caused by PV interconnections. What we've also shown is that the additional data and analysis required to implement these new methods are reasonable, considering their improved accuracy, and also to keep the study effort focused on those cases that are most likely to impact the electric distribution system. Thank you very much.
So one thing I didn't say is I think we're going to try to save all our questions till after everyone is finished. So our next presenter, whoops. So our next presenter is Jaclyn Frank. Jaclyn Frank is a senior research scientist at AWS Truepower. She received her bachelor's degree in meteorology from Valparaiso University and a master's degree in atmospheric sciences from the University of Albany State University of New York. She currently works in the forecast and research department at AWS Truepower, developing methods to quickly process, analyze, validate, and visualize data. Her main focus has been the mesoscale modeling, resource to power conversion, and validation of data sets used in both wind and solar integration studies, and she has served as a technical lead on several such studies. Please welcome Jaclyn Frank.
Thank you for the introduction. I'll be going a little bit in a different direction for this talk. I'll be talking about some data that we modeled for a study in Hawaii, and using that data to show some differences between the ramp characteristics and diagonal profiles between utility scale and distributed PV. First, I should define the size ranges that I'm talking about for this talk. For this particular talk, I will discuss small distributed generation as 0 to 20 kilowatts, the residential systems that you would see on individual homes. Going up to 20 kilowatts up to about 1 megawatt, I'll refer to that as the medium distributed generation or commercial size. And the reason I broke that down is there can be some differences between the two. Going into the utility scale projects, I'll end up breaking those into the small and the large. These ranges can vary quite a bit, but up to about 20 megawatts I'll define as small, and then I'll show some differences between when you get to these very large PV plants. So we modeled these data for the Hawaii Solar Integration Study. This is a collaborative effort with the Hawaiian Electric Company, National Renewable Energy Laboratory, and GE Energy Consulting. AWS Truepower's role in this study was to synthesize 2 years of 2-second PV data for a number of hypothetical plants that could be built in the future, both utility scale and distributed generation plants. The results were validated against actual measurements across the system of network of sensors in Oahu, and the results were reviewed by a team of experts on our technical review committee to ensure that these modeled data are behaving as you would expect actual plants to behave. The goal of the study was to determine how adding solar PV to the grid was going to impact the grid and what potential mitigation measures might need to take place as we get to the pain point in the grid. So what am I talking about with solar ramps? This is probably old news to most of you, but a solar ramp usually occurs when a low-level cumulus cloud moves over a PV array. Oops, you can see that sometimes these cloud edges can be quite sharp, causing instantaneous, very large, very fast ramps. An extreme case of this is shown on the right. This is a point measurement of irradiance at a location in Hawaii. You can imagine if this irradiance were converted to PV output at a particular point, you could have ramps of about 80% of plant capacity in a matter of seconds. So that's what happens at a particular point, but luckily most plants are an aggregate of many different points. So this example shows the impact of plant size. If you say, for example, that a cloud is moving about 10 meters per second, it would take only about 1 second to cross across a single residential PV system. However, if you're looking at a small utility scale plant, that same cloud would take about a minute to pass over. So you can see how the ramp would decrease as parts of the plant are offsetting other parts of the plant, a shaded versus a sunny spot. If you look at a slightly larger PV plant, this is your 100 megawatt plant, that same cloud would take more like 3 minutes to pass across. And then if you look at a neighborhood or a city-wide area of several rooftop systems together, this cloud could take more like 5 minutes to cross. So if you look at the whole island system, like Oahu, for example, a system of clouds is going to take almost an hour to pass across the whole island, so you can really see how a portion of the island would be shaded. It'd be very difficult to have a cloud cross over all systems at once, causing a very large PV ramp. We can look at this a different way. One of the benefits of model data is we can study some situations that probably wouldn't occur in real life. But in this case, we modeled 100 megawatts of PV in a number of different scenarios, both as a single plant shown here, as a system of smaller utility scale plants, in this case 9 to 25 megawatts, and as a large region of distributed PV rooftop systems. And we wanted to see what are the differences in ramps when you model PV these different ways. So this figure shows the frequency of ramp occurrence as a function of plant capacity. You can read these plots as the wider the lines are, that's more frequent large ramps. The blue line here is that single 100 megawatt plant. The red line is the small utility scale systems, and the green line is the system of rooftop PV. You can see in the 1 minute ramps, the large utility scale plant basically has its largest ramps twice as large as the distributed plant. So in this case, it's 14 megawatts in 1 minute for the large plant, and only about 6 megawatts for a minute for the residential PV. Moving on to 10 minutes, you can see now the small utility scale systems have a profile that looks almost like the distributed PV, and now the large utility is almost twice as variable as your smaller utility scale plant. So same amount of PV, but you get, the benefit of geographic diversity here. And moving on to 1 hour, the ramps for all systems are increasing to quite large values. So you might be wondering, seeing these numbers and saying, wow, if you can have a 50% ramp in over an hour period, how is the grid going to handle this? And of course, one of the ways is by planning where these plants are going to be located so that you may benefit from different climatic regions, for example. Another way is by using solar forecasting. Solar forecasting can be used to either predict when a large ramp may occur, or perhaps to give the likelihood of a particularly problematic period coming up. It can use a variety of techniques ranging from sky imagery to satellite imagery to numerical weather prediction models. Obviously, it seems like this could be a more useful strategy for utility scale systems, but it may also be useful for systems of distributed PV, depending on the grid, depending on the market, and so forth. Now, speaking of the grid, the way utility scale and distributed PV impact the grid is quite different. Everything generated at a utility scale plant feeds directly onto the system, and that's that. The distributed PV, on the other hand, anything generated there is usually used at the site, so it impacts the grid more indirectly by decreasing the load at that point. This figure shows an individual feeder over 1 day in Hawaii. The red line is the gross load, or the load that would be expected, whereas the black line shows the actual net measured demand. So the difference between these two profiles is inferred to be the PV that's generated on the system that's actually quite heavily loaded with rooftop systems at this time. So there's really nothing at this point that the grid operator could do to control these rooftop systems. On the other hand, utility scale PV perhaps could be curtailed or something like that if the ramps were getting too large. Another difference between the two can be the diurnal profile. Rooftop systems are often constrained by the tilt and the azimuth of the buildings on which they are built. So you can imagine this figure on the right shows several different orientations across a neighborhood. When you add all of these together, or take the average, you get this black line here. Whereas a larger distributed PV system or a utility scale plant, you can choose your orientation to either maximize the energy, which may be more representative of this blue line here, or you can always configure the system if your particular area has a weather pattern, maybe morning clouds, or you want to match the afternoon load, or so forth. You can choose your orientation to take that into account. Another difference is that utility scale systems have the option of being either fixed systems or tracking, whereas that's generally not practical for your rooftop systems that will most likely be fixed. In this case, we modeled a single-axis tracking plant. It has a horizontal axis and it tracks from east to west to show the differences here. The bottom figure shows the diurnal profile. The fixed system is in blue and it has this smooth kind of parabolic signal, whereas the tracking system comes up earlier in the morning, has a faster ramp, is more flat throughout the day, and then ramps down quickly at night. You can see the difference is even more apparent when you look at the ramp profile. These shoulders of ramps here in the red are for the tracking system, and basically these large ramps that occur more frequently are mostly the beginning and end of the day effects that are generally well known and well predicted. In this particular case in Hawaii, the fixed system had larger ramps, whereas the tracking system, the largest ramp was smaller. So to summarize, we used some data that we modeled for a grid integration study in Hawaii to kind of examine these differences between types of systems in a different way than may be easily done with observed data. We showed the impact of the system size on the ramp distributions, how the ramp size changes as you model 100 megawatts of different types of PV, and then showed some differences in the diagonal profiles and how these might impact the grid. And with that, I guess I'd be happy to take questions at the end of the panel. Thank you.
So our next presenter is Michael Mills Price. Michael received his Master's of Science and Bachelor's of Science in Electrical Engineering from Oregon State University. He is presently a member of the technical staff as well as an engineering manager at Advanced Energy, Inc. in Bend, Oregon. Michael's a registered professional engineer and active member in the IEEE. He currently leads a project team working to develop next generation integration and control technologies with specific focus on energy harvest, levelized cost of energy, and grid support functionality. Please welcome Michael Mills Price.
So I see we have some day 2 show post-lunch atrophy. So if my presentation doesn't excite you, I'll get nods of approval as you guys lurch forward in your chairs trying to maintain awake. So that's a positive thing. So my presentation is going to really focus on, I labeled it commercial, but distribution connected versus utility connected solar. Some of the metrics behind each, and then frame up how the commercial space is really different, right? We're designing this system into an existing electrical distribution system that was primarily designed to serve electricity to customers, and now we're putting generators in that place. And if I can get one thing for you guys to remember from my presentation, it's aggregate response. If we can make these commercially installed PV inverters act in aggregate together, we really start to reap the benefits of this resource. So the image on the top left here is what gets finance people excited about solar, right? It's this growing market, and this is a prediction of what the industry is going to do by market segment over the next four or 5 years here. We see the utility space continue to grow, the large commercial, medium commercial, and small commercial spaces all continue to grow. And on the bottom right, we see why engineers are excited about this space, right? We're finally getting to a point in our industry where we truly need technological advances to continue to integrate these systems into our existing infrastructure. So we see increasing number of installations, increasing system size. I mean, 3 or 4 years ago, we would have talked about utility plants as 5, 6, 7, 10 megawatts. Now we're showing data for hundreds of megawatt power plants, right? We're putting megawatt-size installations on commercial rooftops, Costco's, and that type of thing. So, pretty exciting time to be an engineer in this space as well. High penetration, I think Robert mentioned a number of metrics there, and I think that from a manufacturer standpoint, when the resource starts to cause problems, voltage stability, power quality issues on the distribution circuit, well, that's when we have to come up with a technological solution to help overcome that. So whatever that number is for high penetration, or however that's defined, from a technology development point of view, we're trying to solve challenges here. The advanced services in that bottom graph shows that light blue area, if you can't read it, is reactive power, but I would postulate that that's not just fixed power factor or fixed reactive power support. It's both open and closed loop. And it's different depending on where you're actually installed in our network. Right? In some cases, you don't need advanced closed-loop voltage control. You just need to overcome the VAR load of the native transformer. In other cases, it's really, really important that we do close the loop on voltage. And so there's this mix of technologies depending on where you install and under which area EPS you're actually operating on what your end device needs to do. So a platform of configurable solutions is really what we're looking for. And lastly is capacity factor. I read a IEEE PES article on the way out here. I think it had solar somewhere between 18 and 22%, right? So capacity factor is what you're getting out of the device divided by its nameplate normalized to 24 hours. So we're already limited, right? The sun doesn't shine 24 hours anyway in the US. So we're already limited to 50%-ish on the upper end. But if we start to include reactive power and some of these other types of controls in that capacity factor calculation, well, then we can get it closer to this win number, right? 30, 35%. And these services are things that the end devices can provide. So, to frame up the utility space, I did put some metrics on the top for kind of system size, but again, this is an ever-evolving, changing, murky gray area between commercial and utility. What's different about the utility case is that we're designing these for generation, right? It's engineering services from the ground up. We're designing the infrastructure, the protection, the control. Each individual piece of these large plants are designed to produce power. To do that, we use this hierarchical control strategy, right? You have this top-level, very secure link, fan-out commands on the state of the network to individual inverter master controllers, a term I put up here, right? And that's doing the generator resource management. It's pulling the I/O data from the local transformer, maybe down to subarray kind of monitoring. You're also getting any other pieces of I/O from the field. Above that, you have the data aggregation, you have the system and data security, and again, we're trying to treat these utility plants, I think Kristen Nicole mentioned it yesterday, we're trying to treat these large PV utility plants more like something the utilities are very comfortable with, right? These conventional rotating machines. And we control them in the same way, from the design phase all the way through implementation and then in the operational phase. And with the stuff that we just saw from Jaclyn and other presentations this week, forecasting, system over-design due to the dropping panel prices, and storage integration, seems to be a lot of buzz around storage integration. These three components allow us to do the frequency regulation and the ramp control that's necessary, right? So there's lots of advances. People are figuring out how to do this kind of thing. And it's turning into a traditional generation asset management. And I don't want to take away from how complicated some of this stuff is, but that's how I'm going to bucket it for today's presentation. So I did this mock-up, and your system probably may or may not look different, but if we start at the bottom level, right, there's this inverter master controller. Let's see if I can use the mouse. There's this inverter master controller, and it's controlling a local HMI on the site, fanning out commands to any number of inverters, depending on the plant size. It's pulling data from the transformer, oil temps, that kind of thing. Weather station data is coming in, and then various other I/O field devices. Above that, you have this plant SCADA LAN, right? You might have some ISO rig, Cal ISO, remote intelligent gateway. Sorry for the acronyms, us engineers, we go down tangents sometimes, but remote intelligent gateway might sit on there. I drew a different line here for a third-party data acquisition system, and that'd be a push-only data, right? You're not going to have some third party talking two-way communications on the plant-level SCADA for utility side. You have the utilities remote terminal unit, most likely talking with the substation equipment, the LTC, the relays, the cat banks, and above that you have a very secure home-run communication pipe to the area UPS operator. Right? Again, your system might look different, but this is the basic building block of a utility PV plant. Then we move to the commercial space, or the distribution space, and I'm trying to use those terms somewhat synonymously today. Everything's different, right? Each individual utility is operating their system differently than the guy next door. The equipment that's on those systems is different by the year it was put in, by the relay settings they're comfortable with to meet those customer needs. So we have regulation equipment, load variability, system capacity. You have this variation in actual system owners. Right on the utility side, it's large finance, banks, and then the utility. On this side, it feels that way, but not really. And I'm not trying to make this a financial or process presentation. In fact, I'll avoid it at all costs as an engineer, but there's a unique set of stakeholders in this commercial space too, right? And they're trying to make it economic for them. The standards limitations, I think other groups have done a really good job covering that over the course of this week, but 1547.8 has recognized there is a need to fast track a few things to allow for this closed loop control. Right? And we're doing a very good job of addressing those as quick as possible. Engineers are very wordsmithy, probably not to the legal level, but we do get rather wordsmithy, so things take some time. On the communication side, there's a number of communication standards that manufacturers leverage, but we haven't harmonized on a single standard for the same types of control. So you hear volt bar, you hear power factor, but everyone's register map is still slightly different. So when you go to configure these things, an AE inverter looks different than a SATCON inverter, looks different than a GE inverter, right? And this is causing additional costs in that process and additional delays. And it also creates a lack of confidence, if you will, from the utility to the equipment manufacturer's perspective. Is it going to do what we tell it to do? Why are we when it's different? That type of thing. From a system capabilities, as manufacturers, we do everything we can inside of that 1547-2003, right? We can do open loop control. So you'll see fixed and schedulable power factor and curtailment. Anything where we're not physically closing the loop on the system voltage at the PCC in the distribution space, we do, right? We offer that. We know it's needed, it's necessary, but it's only one step as we move towards this breadth of solutions for the end high penetration environment, right? The last bullet is the most important one from this entire slide, and that is that we are primarily managing every commercial installation as a single standalone asset. The image on the upper right there, each of those nice clip art puzzle pieces could represent a commercial building block, right, or a commercial PV installation. Today, we're managing those as if they're not connected whatsoever. And 500 kilowatts, well, that's not that big. We're not going to get that much voltage regulation out of that. But as we start to add those up in aggregate, you really start to develop a power plant, even across an area EPS or a system feeder. And you can really start to optimize efficiencies associated with that feeder and response if we start treating them in aggregate. So how do we do that, right? We have this number of different configuration environments. We have people controlling voltage on each individual circuit differently. Well, we come up with a configurable platform solution. So we have these voltage support functions, both open and closed loop, and we're really only able to control real and reactive power, right? Inverters can't do much more than that. Real or reactive power or both. We have the voltage and trip points, both in terms of frequency and individual voltage. These sites, some have secure, robust communication, some have some level of 3G, Wi-Fi, some internet connectivity. Others are not going to get connected at all. So we need to have solutions that you can put into individual installs that have deterministic results in lieu of communications. How do we do that? We create a priority control structure, right? So if it's being directly commanded, priority 1, and nice little clouds again on an engineering upgrade slides. Feeling pretty good about that. Directly commanded, right? You're being told to go to a set point that takes priority. Priority 2 would be leveraging, it's a pet peeve of mine, but wide area information. So if you were broadcasting out wide area information from a control area, you could use that information in addition to your local measurement and really start compensating and improving efficiency of that individual feeder, freeing up capacity for the sub-transmission and that sort of thing. Third would be a scheduled operation. So you pre-program a device to run a schedule based on time of day, day of week, or month of year. Even if you don't have communications, you know that device is going to be following that pre-programmed schedule. And lastly, it would just be fixed operation. And there's going to be a number of sites where you don't need reactive power, right? It's okay just to continue to be a watt source. You don't need communications. We have sites that are going to have needs for each of these individual priority control structures, and maybe some, if the communications goes away, it falls to the next level down. And that's what I'm postulating as a path forward until we get this closed loop voltage control. The last thing is this management and configuration tools. And I just wanted to talk about, we show all these functions and features, we get excited about it as engineers, but we can't just hand this over to an installer or to a developer and say, okay, configure it. So we create tools to help navigate people to set these things, to set priority, to set the voltage and frequency support functions, and to do it in a manner that supports the communication infrastructure they have there. So again, we're really looking for that aggregate distribution system response to make this thing look like a large power plant to improve the efficiency and operation of today's distribution circuits. So in closing, commercial scale installations do look and feel differently than utility scale installations today. And I've been trying to avoid the word control on the commercial side and talk about aggregate response, because that's what's important. It's not how we get there, it's that the system does respond to these events in a way that we're comfortable with and the utility is excited about to continue to push our renewable portfolios forward. Thanks.
So our next presenter is Graham Stevens. Mr. Stevens is an associate director with Navigant Consulting. He has over 20 years of manufacturing, consulting, and R&D experience, specializing in bringing a broad range of products from the laboratory into production. He's been heading up Navigant's solar due diligence efforts for the last 5 years, in addition to assisting with Navigant's recent renewable integration efforts for a variety of utilities. These projects have looked at solar integration from technical, market, operational, and cost perspectives. Please welcome Graham Stevens.
Good morning. Today I'd like to present some solar and renewable integration best practices from a utility perspective that encompasses both large-scale utility practices as well as smaller distributed scale practices. And I'm drawing up for this talk on a recent project that we did for Arizona Public Service, a leading solar utility in the Southwest. And they hired us recently to look at their internal operations and how they're integrating renewables into their grid. They're facing 1 gigawatt of solar that they're anticipating installing over the next decade. As you can see, 75% of it utility scale is what's projected, and 25% on the customer side of the meter, so fairly large utility scale operations. And for this project, we benchmarked internally what their practices are to both utilities, other utilities, leading utilities, as well as kind of the technical literature and what was kind of out there as best practices for renewable integration from both solar worlds as well as wind and Europe, which is obviously kind of leading us in terms of renewable penetration. And so in defining renewables integration, we started with looking at internally what's happening with renewables inside the utility. And essentially there are 3 different processes here. Their transmission and distribution process, from planning to interconnection requests and studies to potential transmission and distribution upgrades or modifications. And then how renewable energy projects are actually put onto the grid from a resource planning perspective, project procurement, implementation, and operation perspective. And both of those are going on in parallel with both the distributed side, where customers are coming in and doing those interconnection requests, putting it on the grid, and how does the utility deal with that. And also APS has been doing a number of internal projects where they're taking on all of this and installing renewable projects themselves at a larger scale. And then in parallel and kind of connected to all of these different processes are the regulatory drivers. So there are a number of plan filings, procurement filings, update filings, and annual updates that the utility is constantly dealing with in terms of the regulatory driver, as they're shifting from roughly 2% penetration by load today to more like 10% over the next 10 years. And so the categories of best practices I wanted to present today really reduce costs for utilities in 3 ways. Operational best practices maximize internal efficiency by streamlining operations and reducing risk. The infrastructure best practices that we'll go over minimize overhead. And then finally, the technical best practices that were drawn from other sources minimize operating and spinning reserve costs, especially as you get to higher levels of PV penetration that they're anticipating. So this is our list, and I'm just going kind of through the highlights. This is about a 200-page report that I'm trying to summarize in 10 minutes. But essentially, from an operational perspective, one of the critical pieces is procedures, looking at how each of those individual processes are done, and then codifying a flow chart and putting together some procedures for interconnection requests, for distribution planning, for renewable project procurement, and so forth. And as you get, initially utilities, when they're first starting out, kind of say, well, let's try a project and do that more in an ad hoc fashion. But when you start to get this stream of renewable energy flowing onto their grid, formally documenting those processes, auditing those processes, and really policing that will be critical as they're moving forward to get to higher levels of penetration. As we heard from the last speaker, the interconnection equipment at both the low voltage, the medium voltage, and the high voltage connections can be kind of all over the map. And this starts, at the utility scale projects as well as the commercial scale projects. So standardizing that for the utility internally to make sure that their maintenance personnel can handle each of those pieces of equipment, training for them, and so forth, is really important as they move to the future. On the module warranty side, we're seeing a large number of imported panels and thousands of panels being used by utilities. And the panels themselves, the long-term quality is not readily apparent. They can't pick up a module and say, this is going to last 10 years or 15 years or 30 years. Most of them last a really long time, but monitoring quality actively is something that the industry should do. And one of these best practices here is to use tier 1 suppliers, evaluate that list, and so forth, but also to potentially statistically sample installed modules for some of these tests and just actually test for long-term reliability. Finally, one of our best practices was involving regulatory workflow. One thing that we noticed was that at the end of the year, you have some bunching up of projects. Everybody's trying to get stuff done by the end of the year, and so there's this big lump that kind of goes down the boa constrictor of all the workflow through the utility. And so attempts to best practice here is to try and smooth that workflow via going with smaller, more frequent pieces, early long-term planning, because things can start and stop depending on whether, what laws or what regulatory activities are going on. But trying to smooth that workflow through the utility will help operationally. From an infrastructure perspective, we looked at the different types of costs within the utility that are bigger than any one particular project. And here we found IT systems were very critical and found by all the utilities to be critical, especially as you get up to larger sizes. And coalescing or taking multiple software packages and getting to some level of integration, as well as aligning those packages with your goals and processes will be critical in tracing them back to mission requirements as you move forward to higher penetration levels. On the monitoring side, the monitoring costs at the residential and commercial level are relatively high and relatively complex, as we saw from some of the previous slides. Taking this thousands of residential homes and actually trying to control them as a single power source for utility is somewhat difficult. But as you try and balance electricity supply and demand, that may be what you want, especially as you have more customer-sited essentially power plants installed on your grid. So that's an issue that utilities are kind of wrestling with and trying to figure out how to work with. Similarly, siting, our current methods of doing an internet connection request and then having the PV being installed in various homes are also being installed in various locations at large scale. Doesn't necessarily consider the reliability of the grid for those particular points. And so one of our best practices here was to identify those grid strengths and weaknesses and factor that into the transmission interconnection process, as well as potentially considering pre-approval in some fashion of PV installation sites. And then lastly, in going through the technical best practices, one quote in particular really summarized a key principle of technical renewable integration, which comes from the wind industry but applies directly to solar. And it's this: the entire electrical system is variable both on the supply and the demand side, and both can be predicted. The issue, therefore, is not one of variability or intermittency of a particular technology per se, but how to predict variability and what tools to utilize in order to control the process of constantly matching production to demand. So this principle of matching supply and demand leads you to a number of different ways of handling solar intermittency. So the first, of course, is solar forecasting and looking at the current process or the current packages out there for solar forecasting. The accuracy really is not as high as desired, certainly not as high as the wind industry yet. So we're seeing utilities developing their own software, trying to research more accurate solutions, but this is an area which will improve the amount of PV that we can integrate on the grid. With regards to sudden cloud dips, reducing the interval scheduling, so if we go from utilities tend to schedule power blocks where they turn power plants on or off to match the projected load on an hourly basis or potentially a half-an-hour basis or 15-minute basis. If you can get that interval scheduling down to lower periods of time, you can better match your supply and demand. Demand-side management techniques of having the utility be able to turn off everybody's air conditioner suddenly when a cloud develops might be another possibility in terms of managing clouds. And as we heard from, I think it was 2 speakers ago, where she was talking about how at the residential side or the customer side, utilities don't actively monitor the power outputs on their distribution circuits, but they feel the PV output as sort of a random load reduction, essentially. It's not really random, it's by the day over cycle. But as you get many more residential systems onto your grid, knowing what those systems are doing exactly will help in terms of, again, matching this supply and demand. And so one of our, so this is increasing those links back to the utility. And this is an issue utilities, struggle with, trying to turn those thousands of residential installations into kind of one plant that they can sort of deal with and monitor. Is something we're working towards. And then finally, on the energy storage side, it still seems to be relatively expensive for PV. I was seeing some of the lithium-ion battery solutions by Samsung earlier today, but it still seems a bit expensive. We'll see how that works out cost-wise going forward. And then, of course, for CSP, we are seeing some thermal energy storage techniques being introduced to the marketplace. And again, the costs of those are still in question. Another large technique to reduce your, to improve your cost of grid integration for solar is to increase your level of geographic diversity. As we were saying before, that if you have one large field versus 10 very small fields, the 10 very small fields are distributed over a wide area, tends to help a lot in terms of smoothing out those variations. And this applies also to not only large-scale fields in terms of location of where they are, but also on a feeder. If you get clustering on a feeder, you get the same sort of impacts. And then finally, our last passel of technical best practices is regarding following the lead of the EU. The EU has been leading the US with regards to high levels of penetration, and if we adopted their practices earlier, we can potentially get to higher levels of penetration more inexpensively for utilities and the industry. So going to more of our support and smart inverters earlier, evaluating those cost-benefit trade-offs, of course, looking at low voltage ride-through, which I know is under consideration on the IEEE side, and then looking at financial and legal provisions for utilities to do curtailment for limited periods if it's needed, especially early spring, 10 a.m., where you have really low loads that particular time of the year and very high solar output. Right now, that's not important because you're at 2% penetration for the whole system. It can absorb those variations, but as you get to higher levels of penetration, these sorts of issues might become more important as you get there. So, in summary, the renewable integration roadmap that I was outlining highlights of, and happy to discuss anything in further detail afterwards or questions, really considered these 4 different areas of improvement from the internal people goals to the infrastructure, the internal alignment, and the technical side of renewable energy integration to try and capture that as we move forward. Thank you so much.
So our final speaker is Chris Trueblood. Chris Trueblood is a senior project engineer at EPRI. He is responsible for conducting technical assessments in laboratory and field tests of distributed PV systems. Key areas of study include characterizing solar power output variability, evaluating utility interactive inverters, and assessing PV system performance across varying environments. Chris also implements a data acquisition system and analyzes data related to integrating PV into the electrical distribution system. In this capacity, Chris has developed multiple user-friendly computer interfaces for viewing real-time and historical data. Mr. Trueblood completed his master's degree at Auburn University and is a registered professional engineer in Tennessee. Please welcome Chris Trueblood.
Good afternoon. By show of hands, who enjoys analyzing data? Maybe half almost? So by show of hands, who does not like analyzing data and would rather have someone else do that for them? All right, the rest of you must be asleep. Okay, well today I'm going to show you some analysis of plant performance using 15-minute and hourly data. We're going to look at voltage on some megawatt-sized plants and how the voltage can be moved by increasing the PV output on these plants. And lastly, take a brief look at ramping, plants ramping up and down, and of course, we like to use 1-second resolution data to get the best resolution that we can on these plants. So as we step through this, think about moving from the analog, the older TVs, to the high-definition television. You still get the same image, you still know the score at the end of the ball game, but you get a whole lot more information out of the picture and the show if you have a high-definition TV. So this high-resolution monitoring that we're undertaking, we like to collect 1-second data. We can roll that up to higher periods, but we also get that crisp image that we are looking for and that the utilities are seeking to help better understand the impacts of distributed PV on their circuits. So at EPRI, I work in the program called the Integration of Distributed Renewables. And one of our projects is to conduct a nationwide monitoring. We call it distributed PV monitoring. And currently you can see that we have these 1-second monitoring sites scattered about throughout the United States. Southern Company has led the charge here, and so we see most of the sites are installed in the southeast. We've been creeping up the Atlantic coast. You can see some recent installs. And of course, in California, we are going to be putting some monitoring equipment out there for an upcoming project. So in total, we have about 200 sites collecting this 1-second data, and we started in the end of 2010. For central plants, we're currently monitoring a good handful of about 1 megawatt size plants, and in that we always measure the solar irradiance, the weather. Sometimes if we're able to get into the plant and be more invasive, we will definitely measure DC array parameters, voltage, current, the back module temperature, and of course we always monitor the AC output of the system, either per inverter or an aggregate of the total. One system that's really interesting, and we've been fortunate to literally get the keys to the fence, is a system in Tennessee, and it's a total of 1 megawatt, covers 3.5 acres, has over 4,000 PV modules, and 4 inverters. This system was installed a couple years ago, and we were able to retrofit our instrumentation onto this system about a year ago and collect the high-resolution data. We were able to put in pyranometers throughout the array and also put a single module that is completely independent from the system using a microinverter on site as well. So we can kind of get a 1 module to 1 megawatt comparison. So now I'll use this 1 megawatt site and let you see how this plant is performing since January of this year. So we'll look at about 8 months. We'll start off with solar insolation. So this is how much sunlight is hitting that site, and we're using a plane of array pyranometer. And you can see in January, it's pretty cloudy, as we would expect in Tennessee. As we roll over into the spring and early summer, we have a lot more daily insolation available. And you can see some degradation in July and August, and we suspect that's probably due to excessive amounts of clouds. So southeast, we love our clouds, and they're everywhere. So we're averaging about 4.8 kilowatt hours per meter squared per day over this 8-month period. And that gets the quick thumbs up if you compare to NREL's PV Watts simulator. So that gray shadow behind these bars is the output from the PV Watts. So you can see pretty good alignment on a month-by-month basis, simulated versus measured output. The same plant, let's look at capacity factor. So again, this plant is performing as expected. We do see low capacity factors in the winter, sometimes below 10%. The average for this 8-month period is 0.17, so that's your 17% number. That's close to what you would expect in that part of the country. We are able to get above the 0.2 region in June, and again in August and July we do dip down a little bit. So you can see the same trends as you did with insolation. So the more sun I have, the more energy I get, and that's fairly straightforward. Now what we've done is we wanted to compare, based on the amount of sun that we have and based on the amount of energy that we produced, what's that ratio, or how well is the system performing by compensating for the local sunlight conditions. So we have an equation here, and this is the only equation you'll see from me today, and we'll call it the performance ratio, and it's basically taking the daytime energy and divided by the system rating, so we kind of normalize that energy, and then in the denominator we look at the daytime solar insolation, so that's how much sunlight we had over that daytime period, and we normalize that to 1 sun, or 1,000 watts per meter squared. And what we're trying to do is represent how well the PV system performed given the solar resource. And it's a useful metric to compare relative performance if you're looking at month by month, or if you have different types of systems in the same region, you can see how they're performing relative to each other. So a ratio of 1.0 means I'm operating perfectly, and you may never ever see that, and because you have inverter losses, balance of system losses, module mismatch, etc. So let's look at the graph. From the eight months, you can see we're dancing around in the low 80s on our performance ratio. The green line is our golden egg there. It's our 1.0 target, and the decrease from that is really essentially how you would derate the system if you were planning for it. Higher temperatures that you see in the summer are dancing around the 50 degrees C range, and this is a temperature that's measured on the back of the module, and it's weighted. So at nighttime, we don't care what the temperature is. The more power we get out of the module, the more that factors into the weighting of the weighted average. So mostly you can see a warm module, but not too hot. But you can definitely see a degradation in the summer months on this performance ratio. Next, let's look at get away from energy for a moment, and let's look at the peak power. So for every month, we can look at the 15-minute and hourly intervals of what was generated. And we can take the maximum 15-minute and maximum hourly peaks, and you can see that if the system was performing at its rated condition, based on its nameplate rating, then you should have a peak generation of 1.0, because we like to normalize everything. The month of March had our highest peak, and that was in the mid-90s for 15 minutes. And you can see our hourly values don't really get up to the 90% of our rated capacity. So again, you can see the trend by season. The spring has the highest peaks in late winter, and the lowest peaks are in the summer. There's several explanations. One of them is the angle of the sun. So this system is tilted at 25 degrees, and so it's at approximately maybe 35 degrees latitude. So in the summer, your sun is almost directly overhead, and you're going to get a steeper angle incident on your solar panel. Okay, so let's slice the data a little bit differently, and we'll look at the kind of the seasonal generation profile by hour of day. So we'll take all of the hourly generation values that we have for the winter and spring season, and we'll plot them kind of doing a statistical representation by hour of day. If you can see the mouse, the top line at the top there is representing the maximum hourly output, for each hour. The black line at the bottom is the minimum. So as you can see here, in the winter we have at least one day where it's pretty much overcast the entire day, no output almost. If you look over in the spring, you see even on an overcast day, we still get upwards of close to 20% of our output on peak. Again, the maximum at the top, minimum at the bottom. The blue area in between represents the interquartile range. So it's the 25th to 75th percentile of where we would expect that hourly power to be for this season. And in the winter, you see 0.5 or 50% of the rated condition spanning, and in the spring, you see 25%. So you see definitely a seasonal change from winter and spring operations. So let's look at voltage. And we have some distribution circuits that we're modeling as part of a Department of Energy project, and we'll call them J1 and K1. And these circuits are in the northeast and southeast respectively, and they both serve rural communities. So one thing to note, they both have PV, so 1.7 megawatts on J1, 1 megawatt on K1. The 1 megawatt system that I just showed you, that is the 1 megawatt on K1. You can see in the red bars, substation load tap changers. That's the transformer that's making adjustments at the substation to regulate voltage. Feeder regulators, which are devices on the distribution circuit out from the substation as you go down the line, and capacitor banks. So you can see these two circuits. So we'll look at the 1 megawatt site first. This is again the same plant we've been looking at in Tennessee. And we plotted 10-second average voltage against power. And you can see at nighttime you have 0 power, and the voltage can range quite a bit, nominally 1.01 up to 1.04 or greater. As the PV system output increases, you can see a direct correlation of the more PV you're generating, the higher you're going to push that voltage up. And that's what we would expect given electrical phenomenon. And this is for the entire month of May, so we have about 270,000 data points shown here. The 5% limit is a threshold that you don't want to exceed for planning purposes. Robert mentioned it earlier. Now let's jump over to circuit J1. We saw the circuit characteristics on the previous slide. This has a 1.7 megawatt PV in a couple different places on the circuit. And you can see in the same month of May, we do exceed that planning limit. In fact, quite a bit once we get above 60% of the rated output of the system. So this could actually cause a problem. In fact, it has caused a problem. So the utility has closed this circuit, J1, for new PV systems. They said, no more, that's it. There's concerns, complaints of over voltage, and at a 6 megawatt maximum load, 28% of that could be masked by these PV systems. And additionally, the utility has asked the customer of these PV systems to lower the power factor on the inverters. The idea is to send more reactive power into the system and help control that voltage a little better. Since they've done this restriction, they've had complaints from customers calling, say, why can't I install PV on my roof? I'm just 4 kilowatts. And so they're unhappy because this circuit is closed to new customers. So in just a couple minutes, actually in 1 second, I will show you some 1 second data. Here's a cloudy day on September 29th last year, and we're looking at 1 minute average values, and you can see some good variability here. And we're going to zoom in here, so we're looking at about the 1 o'clock hour in the afternoon, and you can see about a 3% per second ramp down. A minute later, a 3% per second ramp up event. And so we're able to sweep about 75% of this megawatt site in just a half of a minute. Remember, there's that single module that's on the same site. So it's also seeing these similar ramping conditions. We have 3% per second down, but it goes up a lot faster, as you would expect could happen with a single module versus 4,000 aggregated. I'm going to skip to here, and we're going to zoom in. This is looking at 4 minutes. You can see, remember I said that we had 8 pyranometers scattered around the plant. We can definitely see kind of a wave effect as clouds pass over the plant. The orange line representing the aggregate irradiance from those sensors, the gray line showing individual pyranometer values. You can also see a good correlation between AC power production, which is the 1 megawatt output, compared to the aggregate of the 8 pyranometer systems. So thank you, and future work that we're doing is taking it to the next level with ramp rates, looking at statistical distributions, how different sites are correlated over different regions. So our work is really kind of just beginning, and so we're really excited to be a part of it. Thank you.
So let's jump into questions. I always have questions, but I think we have 15 minutes to go here, and so I want to make sure we get all the audience questions. So if you have any questions, please step up to the mic and ask our esteemed panel.
Hi, my name is Matthew Williams. I'm a data scientist at Locust Energy. We're a solar monitoring and analytics firm. My question is for Jaclyn. We did a very similar study to what you did, focusing in LA, where we had a large concentration of systems. It was on 5-minute data, so not 1 second data or 2 second data like you had. My question is, you stated that ramp rates could be reduced to geographic variability. But I wanted to know if you took a look at the number of systems, how that impacted the variability of ramp rates.
Yeah, I mean, it depends. If you have a bunch of systems that are closely spaced together, I would expect that would have less of an impact than fewer systems farther spaced. Just so that you could have, a cloud system moving in that may be covering, 3 of your systems at once, the other 3 may be unshaded at the same time. Whereas if all your systems are clustered together, they'd be impacted by the same weather simultaneously. So it probably depends a little bit on what type of configuration you're looking at, but yeah. Did you find something different, or?
Within our data set, we found that that the number of systems played a larger role than geographic distance. That even within like a 10 by 10 kilometer area, that you could capture most of the volatility reduction versus even extending that out to a 20 by 20 kilometer area. Thank you.
I actually had a follow-up on one of your topics, Jaclyn. So in your deck, you give an example that sort of was a theoretical example, kind of assuming a homogeneous cloud block. I'm assuming the actual ramp rates you were calculating were based on actual weather. Was that correct, or modeled weather? And if the latter, what was the spatial resolution of the grid cell?
Yeah, I didn't really go into how we created these data. We ran a numerical weather prediction model at 1 kilometer resolution down to about 10-minute output. And then on top of that, of course, you can't possibly simulate actual clouds at that scale. I mean, the clouds are smaller than your grid spacing. So we developed we call it the stochastic kinematic cloud model. It's sort of like a representation of clouds that could be occurring within that grid cell. And those clouds are allowed to evolve and advect based on the modeled wind speeds and so on. I have a paper on that. We can talk about it more later if you'd like. But it was tuned to actual measurements to make sure that we're getting variability accurate.
Want more questions? All right, well, I will ask a question. So, I think we have several of the speakers focused just on distribution, and several kind of looked at both. I mean, based on, as I mentioned at the beginning, I think at the very first session we had, there was some talk about where you saw more of PV installations going. Would they be going on the distribution side, commercial, or on the utility side? I know some had felt more on the utility side. There was some mention at that meeting about as prices fall, maybe more would be going on the distribution side. I'd be curious, just from your feeling, from this panel's feeling, about where do you see, like, maybe the next 3 years and maybe beyond, where PV installations will be focused and why? One more. There's pass the mic.
That's the mic's here. I guess I could take a stab at that. But as an engineer, I hope both. I know that's not the answer you're looking for, but we have a tremendous amount of commercial rooftop space out there that's this perfect asset, and if we can just grid policy and get the financing in place, it's right at the load, right? That's where we're consuming this stuff. It's a perfect spot. We also have these giant deserts down in the Southwest where a couple 100 megawatt power plants seem to make sense. So I really believe both is the answer. Maybe it doesn't help distinguish one or the other. But we're excited about both, especially in the commercial, the larger commercial, these areas where not only the system size, but the impact to the grid is much bigger. Right? It doesn't take that many large commercial installations to add up to hundreds of megawatts. And so that's where we can really start to impact the grid and really start to use this energy from the sun, which is why we're all here.
I'll take another stab as well. I guess what we've been seeing in the marketplace, and Navigant does do a lot of market research around these questions, is that the utilities have been in the U.S. have renewable energy standards that they are all slated to meet at this point, and so they've sort of bid off a fairly large chunk of project flow that's sort of set in place now for the next few years that they're busy installing. So we don't expect beyond those requirements to see a lot of new or above that utility installations unless the laws and unless those renewable energy standards change, which is possible, of course. And then aside from that, we're sort of seeing commercial installations because of the, if you think about the overhead associated with, say, a 100 kilowatt plant versus the overhead associated with a 3 kilowatt house, you have a lot lower overhead costs. You've got the same sort of selling costs for each of those 100 houses or 20 houses to make up 100 kilowatts. So we're seeing more commercial installations than residential, so roughly 33% to 2 to 1 commercial or residential, and that of course fluctuates depending on incentives and local conditions. So there's a chicken in each pot, I guess, to replicate that. That's what we're saying.
Robert, you want to take a shot at it?
Well, I think to add on to what Graham just said, I think if the RPS standards are continuously ramped up and continuously increase, then we're going to see most of that megawatts coming in at utility scale. I think that if the price of PV keeps going down, the distributed will continue to grow just as the economics, life cycle costs make it affordable for each homeowner to make that decision whether they want to invest in the next 20 years worth of energy versus paying the next utility rate case increase. So I think it really will be driven primarily by policy as long as the price of PV keeps its downward motion.
So Jaclyn, maybe from a forecasting standpoint, do we think we can forecast a bunch of little tiny systems pretty well and be able to understand what their impacts will be on the overall system?
Of course, it's something that's evolving every day. Forecasts are constantly being improved. In Hawaii, for example, when you're looking at a grid that's isolated and you have large systems where there's a system on almost every house in Hawaii. I mean, forecasting not for individual rooftop, I mean, that's not going to happen. But if you can perhaps forecast at a feeder level or at a substation level, and I think that's something that makes more sense.
Chris, maybe from you're the man who collects all the data, the data bearer. How much data do we need to make integrating into the distribution system more simple than it is maybe today in terms of going through the interconnection processes and making sure we understand the impacts at high penetration?
Right, I think we need enough data to gain the general knowledge that we need to understand the 15% rule. If we're going to change that, well, what are the implications? And if we're going to model feeders like this J1 and K1 feeder that I spoke about, how many of those feeders do we have to model on the computer system and run different scenarios to understand general characteristics? So, we've thrown out numbers like 30 feeders or 40 feeders or whatever, but we don't know what the magic number is. But for every feeder that we model, we like to always validate that with ground-based measurements. So the more data, the better, but if you're swimming in data always and you can't draw conclusions from it, then it's kind of washed out.
Right. Bill, I know we couldn't keep you away from a mic.
That's a question for Chris. On that northeast feeder where you're having voltage issues, were you looking at reaction of what the low tap changers were doing at the same time, or were they fighting it? Were they backing off? Because it seems like there was maybe more control on that circuit than there was on the 1 megawatt circuit, and so it seemed there was a lot more fluctuations on that particular circuit.
Yes, and that's one reason that I showed the 10-second average voltage. And a lot of the line regulation equipment, like voltage regulators, they won't make a setting change in maybe 30 or 45 seconds once they're sensing the voltage, and if it's above their trip or step threshold, then they'll make a change. But there'll be 30, 45 second or even a minute period before it makes that change. So if we look at, we also have voltage measurements at different points along the circuit. So the graph that I showed you was at the point of common coupling for these large plant. And if you look at the voltage at other points along that same circuit, you can definitely see some stepping due to the voltage regulators. And the voltage elsewhere on the circuit is being held, within bounds, but at the cost of more tap changer operations, more step changes on the voltage regulators. The question is that going to wear out the equipment sooner than it should otherwise? And what other implications is that for the utility? So yeah, the stuff is working elsewhere on the feeder, but at that site, you can definitely see, if you're below that 30-second threshold on a time interval, you can definitely see the movement that I showed on the graph.
And a follow-up on the ramp rates you were talking about, 3% per second, which is not that high for a larger plant. The question is, was the main concern voltage flicker, or what were they? What are you trying to get at with your ramp rates and things like that?
The ramp rates we're looking at kind of how multiple sites are correlated. So we have a megawatt here, a megawatt there, a megawatt somewhere else, and each is ramping, based on those local cloud movements. How well is that correlated? And so that's the sort of analysis that I wish I could show today, but that's my job. so we'll be, as soon as we get results out, we'll definitely share what we can with the public. But the distribution, statistical distribution of ramping rates, and the distribution utilities are interested to see, well, if I have this dispersed PV, is it going to be ramping simultaneously, or is it essentially random and kind of washes itself out? You've seen from the other presentations that can definitely happen, but to what extent does that happen, and in different geographic regions, it may happen differently.
We did not see flicker problems at either side. We were using a flicker meter in electrical.
Yes, we did look at flicker, and it's flicker is on an order of magnitude faster than PV moves, so it was not.
It's always been a question, so that's good data. I think the utilities are concerned that these things are going to turn on and off really fast to cause flicker, and they just don't.
Right.
Well, we've run out of time actually, so please thank the speakers. They did a great job. If you have more questions, hopefully they'll stay here long enough before Clinton's talk, so come and grab them.